Next, it'll be worthwhile to consider a detailed example to set the stage by illustrating the kinds of mathematical techniques that we were using. So here's a classic application for the analysis of algorithms. In a very ubiquitous structure in computer algorithms and implementations is a binary tree. And so one question that arises is, how many bits do you need to represent a binary tree with n internal nodes? And there's many applications of this. For example, there's data compression algorithms that involve building a code that's represented with a binary tree and then transmitting the binary tree. And you want to do it with the least number of bits. So the answer, which is kind of direct from information theory, is that if you know the number of different binary trees with n internal nodes, then you need log base 2 of that many bits, because otherwise you couldn't distinguish between, there'd be two trees you couldn't distinguish between. So you need at least log base 2 Tn, where Tn is the number of binary trees with n internal nodes. So then the question reduces immediately to a counting question. How many binary trees are there with n internal nodes? So that's a classic application of analysis of algorithms. We have this practical problem and we want to solve this counting problem. So the first step in the classic analysis of algorithms is to go ahead and develop a recurrence relation. A binary tree is a recursive structure where you have a node that has exactly two subtrees, a left subtree and a right subtree. If there's k nodes on the left, then there's n-1 k nodes on the right. So we can write down this mathematical recurrence relation on the bottom left there. T sub n is equal to the sum for all k between 0 and n-1 of the product of these two. You can have any tree on the left and any tree on the right. And then we add a Kronecker delta for 0 because we say there's exactly one binary tree with 0 nodes to make the recurrence work. And over on the right here is the small cases. It's showing there's one tree with one node, two trees with 2 nodes, 3 trees with 5 nodes, 14 trees with 4 nodes, and so forth. So that's the first step, develop a recurrence relation. Now the next step is to introduce what's called a generating function to try and solve that recurrence relation. Use that mathematical relationship to try to get an explicit expression for the number of binary trees of n nodes. And the generating function is just sum for all n, the number of trees with n nodes, times z to the n, where z is a free variable. T of z is defined to be the sum for all n of t sub n z to the n. So on the right-hand side, we have a double sum for n greater than or equal to 0, and then the recurrence, tktn minus k sub over k times z to the n, and then the delta n 0 just reduces to a 1. Now we have an expression for t of z, and what we're going to do is manipulate the sums on the right-hand side to express them in terms of t of z. And the way to do that is to switch the order of summation, put the sum on n inside, the sum on k outside. So it's the sum all positive k, sum n bigger than k, tn minus k, tk, tn minus 1 minus k, z to the n. And then the next thing you can do is change n to n plus k plus 1, and that'll allow us to separate the sums. So t n minus 1 minus k becomes t sub n, z to the n becomes z to the n plus k plus 1, and now that allows us to distribute and separate the sums. So t of z equals 1 plus z, sum on k, tk z to the k, sum on n, tn z to the n, and both of those are nothing more than t of z. So we have an explicit relationship on the generating function. T of z equals 1 plus z t of z squared. So starting with the recurrence, we end up with a functional equation that the generating function must satisfy. That's the second step in classic analysis of algorithms. Now the third step is to take that functional equation and use it to extract the coefficients to tell us what Tn is. That's what we're after. So the functional equation is from the last slide. T of z is 1 plus z, T of z squared. We can use a quadratic formula to solve that. So it's just a quadratic in T of z. Just manipulating the algebra, it turns out to be 1/2, 1 plus or minus square root of 1 minus 4z. And it has to be minus out of the two choices to make it come out right for n equals 0. And then 1 minus 4z, that's 1 minus 4z to the half power. So we can use the binomial theorem, or the generalized version of the binomial theorem due to Newton, to express that as 1/2 choose n, the generalized binomial coefficient, minus 4z to the n summed over all n. So that's direct from the generalized binomial theorem. Now, there on the left-hand side, our coefficient is t to the n. On the right-hand side, well, we have to make a variable change to n plus 1. But setting coefficients equal, now we have this explicit expression for t sub n. Minus 1/2, 1/2 choose n plus 1, minus 4 to the n plus 1. That's an explicit expression for the number of binary trees with n nodes. Now we can simplify that using the definition of the generalized binomial coefficient. On the bottom you have the n plus 1 factorial, and on the top you subtract 1, 2 up to n plus 1 from the 1/2, and so we get this expression here, which looks a little bit unwieldy, but it's not too difficult. The next thing we can do is, out of the minus 4 to the n plus 1, you take minus 2 to the n and put them into those factors, and you get the odd numbers. And then there's a 2 to the n left over, and another one goes to cancel out the 1/2. So you can check that. That's just arithmetic. And now we're getting close to a pretty simple expression, because what you can do is write the 2 to the n as 2 over 1, 4 over 2, 6 over 3, and like that. And now on the top, we're going to have 2n factorial. On the bottom, we're going to have another n factorial factor. And that gets us down to an explicit solution. T sub n equals 1 over n plus 1, 2n choose n. These are famous numbers known as the Catalan numbers, and this solution's been known for a few centuries. That's the third step in classic analysis of algorithms. So now our question was, how many bits do we need to represent a binary tree with n internal nodes? And our answer is, you need at least log of the Catalan numbers bits. But that's not quite a satisfactory answer. If you've got a programmer that's trying to figure out how to do it for 1,000 nodes, you've got to figure out how to calculate the number of bits from that expression. Or it's for 1,000,000 nodes. It's not so clear. You maybe need some expertise in numerical analysis. And when you think about this sort of problem, people today think, well, once I have a mathematical expression, I can just call a math package and get the answer. And that's maybe sort of the case of having a computer or calculator do it. But think back to the classical mathematicians in the 18th and 19th, 17th, 18th, and 19th centuries. They had to do all these calculations by hand. And so they're looking for really efficient ways to calculate things, not using a computer at all. And in fact, what's called asymptotics or asymptotic estimates has been really played a central role in scientific calculations for centuries. And so there's a vast array of techniques available to us to do a little bit better job than giving a complex mathematical expression. And perhaps the most famous example of that is Stirling's approximation, developed in the 18th century. And it says that log of n factorial is about n log n minus n plus log square root of 2 pi n. And actually that square root of 2 pi was not known for quite a while. That was Stirling's contribution. And it's a very accurate approximation and a lot easier to compute than log of n factorial. Even for 100, So this table just gives what the 460 is n log n, the 360.52 is what you get when you subtract n, 363.74 is what you get when you add in log of square root of 2 pi n. So it's very close even for 100. And for large n, it remains very close. For 1,000, it's accurate to within 2, and for 10,000, it's still very close. Extremely accurate approximation to log of n factorial. And the rationale for using approximations of this sort is that we can get very precise numbers, which is really what the scientist wants, for specific values. Not only that, we get, using just a few standard functions, we get concise representations of the functions that we care about that are in a canonical form that we can work with. And not only that, by adding more terms, we can have what's called asymptotic expansions, where we can get the accuracy we want just by adding more terms. And all the methods that we consider have that property. And this was developed over and used successfully over many years by many scientists and mathematicians. Just mention a few, Euler and Poincaré and de Broglie, just from different centuries, but there's many, many others that have developed and work with asymptotic expansions. And they play a key role in the analysis of algorithms. For example, for our problem, we have this solution 1 over n plus 1, 2n choose n. And actually, to put it in a convenient form for applying Stirling's approximation, we just write that as e to the log of it. And so the log of 2n choose n is log of 2n factorial minus 2 log of n factorial. And then there's a minus log of n plus 1 for the 1 over n plus 1. And now we can apply Stirling's approximation to the first two terms. And the second term is very close to log n, of course. So just substituting that in, we get a long expression. Log of 2n factorial, just using Stirling's approximation, is about 2n log 2n minus 2n plus log square root of 4n. And then the next 2 log n factorial, that's the next term, 2 n log n minus n plus log square root of 2 pi n. And then there's a minus log n. And now it's just a little bit of algebra, just to practice your algebraic ability. Just check that this is true. So log of square root of 4 pi n minus 2 log of square root of 2 pi n equals minus log of square root of pi n. So with a pencil and paper, you can figure that out. And then the 2 log 2n, most of it cancels. And all that's left is 2 n log 2 minus the square root of log pi n minus the log n. And then if we undo the x log, we get that asymptotic estimate for the number of binary trees with n nodes. And that's a very accurate asymptotic estimate. It's very close to, very, very close to 1 over n plus 1, 2n choose n. But it's much more useful. We can, and if we want more accuracy, we could get it. But that's in a standard form, and even by hand you can compute values. Or if you want to answer our question, how many bits do you need for a binary tree with n internal nodes? You can answer it directly. It's about 2n minus 1.5 log base 2 of n. And even a working programmer is going to say, oh, that's a little less than 2,000 bits for n equals 1,000. And by the way, it's actually easy to represent a binary tree with 2n bits. You just do a pre-order traversal and output a 0 when you hit an internal node and a 1 when you hit an external node. So that kind of answer is very satisfying to our programmer. You can do it with a little less than 2n bits. You can do it with 2n bits, and the best you could possibly do is a little less than 2n bits, and that's the kind of answer that we want to see. So that's a very classic application of analysis of algorithms. And particularly in the 60s and 70s and even the 80s, there were a wide variety of problems that needed to be studied in this way. So that's the basic summary developer recurrence relation. Derive an equation on the generating function. extract the coefficients, do an asymptotic approximation, classic techniques in analysis of algorithms. And so when Philippe and I started our careers, we had learned this. We knew the math, well, we learned more math and are able to do this and able to attack many, many problems. But our challenge was that we had to face the idea of teaching this stuff to computer science students. And particularly as the years started to wear on, we got into maybe 1980, the students had lots of computer science, but not so much math. So a challenge that we face just in furthering our being successful as teachers and researchers is how are we going to efficiently teach this stuff to CS students? This is the type of thing that anybody who wants to use a computer effectively really needs to know how we're going to teach it to CS students. So that's the first major theme in the story. We knew the math, we knew how to analyze the algorithms, how we're going to teach other people to do it.